Whether you're just learning density or reviewing for an exam, this is a skill that shows up everywhere in chemistry. In this video, we're going to solve density problems step by step, from basic calculations to real-world applications you'll see on tests and in labs. We'll start with simple one-step density problems, then move into unit conversions, comparisons, and displacement scenarios. For every problem, I'll show you how to set it up, track your units, do the math, and check your answer with proper significant figures. So grab your calculator, pause when you need to, and let's get started. Before we start solving problems, let's make sure we understand what density actually means. Density describes how much mass is packed into a given amount of space. In chemistry, we define density as mass divided by volume. If two objects have the same volume but different masses, the one with more mass is denser. And if two objects have the same mass but different volumes, the one with the smaller volume is denser. A larger density value corresponds with a more dense object. Density is important because it helps us identify substances, predict whether something will float or sink, and connect mass and volume in real-world situations. Density is also an intensive physical property. That means a pure substance has the same density no matter how much of it you have, as long as temperature stays the same. There are three big ideas you need to remember about density. Density always relates mass and volume with the equation density equals mass divided by volume. Units matter. Density units are mass per volume, like grams per milliliter or grams per cubic centimeter. Milliliters and cubic centimeters equal the same value. The conversion factor to convert between them is 1 milliliter equals 1 cubic centimeter. You can rearrange the density equation to solve for mass or volume. You can also use density as a conversion factor to cancel out mass or volume to get to the other. So if we had grams initially, we could divide the density value to cancel out grams to get to milliliters or cubic centimeters. And if we had milliliters or cubic centimeters initially, we could multiply by the density value to cancel out milliliters or cubic centimeters to get to grams. Once you understand those ideas, density problems become very predictable. As you work through these problems, remember, density problems aren't about memorization, they're about setup. If your equation is correct and your units cancel out, the math will take care of itself. Pause when you need to, write out your units, and focus on understanding each step. In this first category, we're working with basic density calculations. You'll either be given mass and volume and asked to find density, or you'll be given density and one other variable and asked to solve for the missing piece. The key here is recognizing which form of the density equation you need and making sure your units match. These are typically one-step problems, but they're foundational. If these feel solid, everything else becomes much easier. Number 1. Calculate the density of a substance with mass 45.0 grams and volume 15.0 milliliters. To calculate density, we use the formula density equals mass divided by volume. The given mass is 45.0 grams, and the given volume is 15.0 milliliters. Dividing 45.0 grams by 15.0 milliliters gives a density of 3.00 grams per milliliter. Number 2, a metal cube has a mass of 100 grams and a side length of 2.0 centimeters. What is its density? First, we need the volume of the cube. The volume of a cube is found by cubing the side length. 2 centimeters cubed means 2 times 2 times 2, which equals 8.0 cubic centimeters. The mass of the cube is 100 grams. To find density, we divide mass by volume. 100 grams divided by 8.0 cubic centimeters equals 12.5 grams per cubic centimeter. The density of the metal cube is 13 grams per cubic centimeter with the correct number of significant figures. Number 3. If a liquid has a density of 1.25 grams per milliliter, what is the mass of 250 milliliters of the liquid? Here, we are solving for mass, so we rearrange the density formula to mass equals density times volume. The density is 1.25 grams per milliliter, and the volume is 250 milliliters. Multiplying 1.25 by 250 gives 312.5 grams. The mass of the liquid is 313 grams with the correct number of significant figures. We can also use density as a conversion factor. The density value can be rewritten as 1.25 grams per 1 milliliter. Creating a unit map, we can start with milliliters and convert to grams using the density value. Setting up the conversion, we start with 250 milliliters over 1. In the next fraction, 1 milliliter goes on the bottom and 1.25 grams goes on the top. Units cancel and we are left with grams. Multiplying the values, we get 313 grams. Number 4, determine the volume of a sample with density 0.789 grams per milliliter and mass 25.0 grams. To find volume, we rearrange the density formula to volume equals mass divided by density. The mass is 25.0 grams and the density is 0.789 grams per milliliter. Dividing 25.0 by 0.789 gives approximately 31.7 milliliters. The volume of the sample is 31.7 milliliters. We can also use density as a conversion factor. The density value can be rewritten as 0.789 grams per 1 milliliter. Creating a unit map, we can start with grams and convert to milliliters using the density value. Setting up the conversion, we start with 25.0 grams over 1. In the next fraction, 0.789 grams goes on the bottom and 1 milliliter on the top. Grams cancel out, and dividing the values, we get 31.7 milliliters. In the second category, we're still using the density equation, but now units become the main challenge. You'll see density expressed in different units like grams per milliliter, grams per cubic centimeter, kilograms per cubic meter, or even pounds per cubic feet. The chemistry doesn't change. We are still working with mass divided by volume, but we'll use dimensional analysis to convert units carefully and consistently. A big idea to remember here is that 1 milliliter is equal to 1 cubic centimeter, which makes mini density conversions much simpler than they look. If you need to have cubic units in the conversion, you can cube the normal conversion as well. For example, if I needed to convert from cubic centimeters to cubic meters, I know there are 100 centimeters in 1 meter. I can then cube both values to make it cubic centimeters and cubic meters for the conversion. Number 5. Convert the density of water from 1.00 grams per milliliter to kilograms per cubic meter. We can start by creating a unit map for both mass and volume. We need to convert grams to kilograms and milliliters to cubic meters. Converting from grams to kilograms will be a base unit to prefix conversion where we only need one step. We will use the conversion factor 1,000 grams for every 1 kilogram. To convert from milliliters to cubic meters, we can first convert to cubic centimeters and then cubic meters. There is 1 milliliter for every 1 cubic centimeter, and there are 100 centimeters in every 1 meter. We need to cube both top and bottom to make it cubic units. Setting up the conversion, we start with 1.00 grams over 1. We could cancel out grams first or milliliters first. Any order will be okay. I will start by canceling out grams first. In the next fraction, 1,000 grams goes on the bottom and 1 kilogram on the top. Grams cancel out and we have our end unit kilograms that we need. We can now look at converting milliliters to cubic centimeters. In the next fraction, 1 milliliter goes on the top and 1 cubic centimeter goes on the bottom. In the next fraction, 100 cubed centimeter cubed goes on the top and 1 meter cubed on the bottom. Milliliters cancel out and cubic centimeters cancel out, and we are left with cubic meters on the bottom. Multiplying and dividing all values, we get 1,000 kilograms per meter cubed, or 1.00 times 10 to the third kilograms per meter cubed with the correct number of significant figures. Number 6. A substance has a density of 2.7 grams per cubic centimeter. Convert this to pounds per cubic foot. We can start by creating a unit map for both mass and volume. We need to convert grams to pounds and cubic centimeters to cubic feet. To convert from grams to pounds, we can use a common conversion factor where we use kilograms in between. There are 1,000 grams in 1 kilogram, and there is 1 kilogram in 2.2 pounds. To convert from cubic centimeters to cubic feet, we can first convert to cubic inches and then cubic feet. There are 2.54 centimeters in 1 inch, and we can cube both top and bottom to make them cubic units. There are 12 inches in 1 foot, and we can cube both top and bottom to make them cubic units. Setting up the conversion, we start with 2.7 grams over 1 cubic centimeter. We could cancel out grams first or cubic centimeters first. Any order will be okay. I will start by canceling out grams first. In the next fraction, 1,000 grams goes on the bottom and 1 kilogram on top. In the next fraction, 1 kilogram goes on the bottom and 2.2 pounds on the top. Grams cancel out and kilograms cancel out, and we are left with pounds, the unit we need on the top. We can now look at converting cubic centimeters to cubic meters. In the next fraction, 2.54 cubed centimeters cubed goes on the top and 1 inch cubed goes on the bottom. In the next fraction, 12 cubed inches cubed goes on the top and 1 cubic feet goes on the bottom. Cubic centimeters cancel out and cubic inches cancel out, and we are left with cubic feet, the unit we need for the bottom. Multiplying and dividing all values, we get 170 pounds per cubic feet with the correct number of significant figures. Number 7. What is the density of a material in grams per milliliter if it is 2,700 kilograms per cubic meter? We can start by creating a unit map for both mass and volume. We need to convert kilograms to grams and cubic meters to milliliters. Converting from kilograms to grams will be a base unit to prefix conversion, where we only need one step. We will use the conversion factor 1,000 grams for every 1 kilogram. To convert from cubic meters to milliliters, we can first convert to cubic centimeters and then milliliters. There are 100 centimeters in every 1 meter. We need to cube both top and bottom to make it cubic units. There is 1 milliliter for every 1 cubic centimeter. Setting up the conversion, we start with 2,700 kilograms over 1 cubic meter. We could cancel out kilograms first or cubic meters first. Any order will be okay. I will start by canceling out kilograms first. In the next fraction, 1 kilogram goes on the bottom and 1,000 grams goes on the top. Kilograms cancel out, and we have our end unit grams that we need. We can now look at converting cubic meters to cubic centimeters. In the next fraction, 1 meter cubed goes on the top and 100 cubed centimeter cubed goes on the bottom. In the next fraction, 1 cubic centimeter goes on the top and 1 milliliter goes on the bottom. Cubic meters cancel out and cubic centimeters cancel out, and we are left with milliliters, the end unit that we need on the bottom. Multiplying and dividing all values, we get 2.7 grams per milliliter with the correct number of significant figures. In the third category, density becomes a tool instead of just a calculation. We'll use density values to identify unknown substances and compare materials to see which one is more or less dense. This is where density tables come into play. We can use a density table to identify the unknown substance by matching the values. When comparing densities, you don't need to overthink it. The larger numerical value simply means greater density. Number 8, identify the substance with mass 120 grams and volume 68.97 cubic centimeters using known density tables. First, we calculate density by dividing mass by volume. 120 grams divided by 68.97 cubic centimeters equals 1.74 grams per cubic centimeter. Looking at a standard density table, a density close to 1.74 grams per cubic centimeter corresponds to magnesium. Based on density alone, the substance is most consistent with magnesium metal. Number 9, which is denser, ethanol or glycerol? Ethanol has a density of 0.789 grams per milliliter, while glycerol has a density of 1.26 grams per milliliter. Since 1.26 is greater than 0.789, glycerol is the denser substance. Number 10. Rank 3 objects by increasing density. We can first calculate the density value for each object by using the equation. Density equals mass divided by volume. Object A has a mass of 20 grams and a volume of 10 cubic centimeters, giving a density of 2 grams per cubic centimeter. Object B has a mass of 15 grams and a volume of 5 cubic centimeters, giving a density of 3 grams per cubic centimeter. Object C has a mass of 25 grams and a volume of 15 cubic centimeters, giving a density of about 1.7 grams per cubic centimeter. Ranking by increasing density will be from lowest density to highest and will correlate with lowest to highest value. The order is C, A, B, with B having the highest density value. In the fourth category, we're applying density to real-world scenarios, specifically volume displacement. When an object is submerged in water, the volume of water displaced is equal to the volume of the object. This allows us to find the volume of irregularly shaped solids that can't be measured with a ruler. Once we know mass and displaced volume, we can calculate density and even determine whether an object is pure, mixed, or made of a specific material. Number 11. Will a metal with density 7.9 grams per cubic centimeter float in mercury, which has a density of 13.6 grams per cubic centimeter? An object will float if its density is less than the density of the liquid. Since 7.9 grams per cubic centimeter is less than 13.6 grams per cubic centimeter, the metal will float. Yes, the metal will float in mercury because it is lighter than mercury, which is denser. Number 12. A gold bar has a volume of 500 cubic centimeters. If gold's density is 19.3 grams per cubic centimeter, what is its mass? To find the mass, we can use density as a conversion factor to convert between cubic centimeters and grams. Setting up the conversion, we start with 500 cubic centimeters over 1. In the next fraction, 1 cubic centimeter goes on the bottom, and 19.3 grams goes on the top. Cubic centimeters cancel out and we are left with grams, the unit needed for the end answer. Multiplying the values, we get 9,650 grams. Number 13. A crown weighs 630 grams. When submerged in water, the volume rises from 250.0 milliliters to 310.0 milliliters. What is its density and is it pure silver? We can calculate the density if we know the mass and the volume of the crown. We are given the mass, but we need to find the volume of the crown by subtracting the final volume of the water minus the initial volume of the water. The volume of water displaced is 310.0 minus 250.0 milliliters, which equals 60.0 milliliters. Since milliliters are equivalent to cubic centimeters, the volume of the crown is 60.0 cubic centimeters. Dividing 630 grams by 60.0 cubic centimeters gives a density of 10.5 grams per cubic centimeter. Because this matches the density of silver, the crown is consistent with being pure silver. Number 14. A student places a solid in a graduated cylinder. The water level rises from 40.0 milliliters to 77.0 milliliters. The object's mass is 92.5 grams. What is its density? We can calculate the density if we know the mass and the volume of the solid. We are given the mass, but we need to find the volume of the solid by subtracting the final volume of the water minus the initial volume of the water. The volume displaced is 77.0 minus 40.0 milliliters, which equals 37.0 milliliters. Dividing 92.5 grams by 37.0 milliliters gives a density of 2.5 grams per milliliter. The density of the object is 2.50 grams per milliliter with the correct number of significant figures. Number 15. An object is submerged in water and the volume increases from 60.0 milliliters to 100.0 milliliters. If its mass is 180.4 grams, identify the material using density charts. We can calculate the density if we know the mass and the volume of the object. We are given the mass, but we need to find the volume of the object by subtracting the final volume of the water minus the initial volume of the water. The displaced volume is 100.0 minus 60.0 milliliters, which equals 40.0 milliliters. Dividing 180.4 grams by 40.0 milliliters gives a density of 4.51 grams per milliliter. According to common density charts, a density around 4.51 gram per milliliter is consistent with titanium.